Привіт! Я Rustem Arzymbetov. Для тих, хто мене не знає, я інженер в Google Play Search Infrastructure Team в Mountain View. І сьогодні я вам розповім про TensorFlow. Але перш ніж розпочинати, я хочу передати окремий привіт усім українським GDG і Володимиру Іванову. Привіт, друзі! All right, guys. So I'm Rustem Arzymbetov, just repeating the same in English. I'm a software engineer at Google, Mountain View, playing on the Play Store search infrastructure team. And I'm going to be talking about TensorFlow today, and I'd like to say hi to all of the Ukrainian GDGs. Well, all of the GDGs here, in fact, and Vlad, who is the main reason why I'm here today. So, hi, guys. All right, so TensorFlow, as a lot of you know, is Google's currently open source machine learning library, which was released in November 2015 and is specialized in the deep learning. It's been widely accepted by developer community as well as research, and currently available under Apache 2.0 license. So I said deep learning. So let me ask you a quick question, in fact, two questions. Can you guys raise your hand if you know what machine learning is? All right, plenty of hands. That's a good sign. And can you also raise your hand if you guys know what deep learning is, what it's about? Okay, far less hands, but all right, let's try to fix that. So what I'm going to be talking today is basically three things. I'm going to talk about deep learning. I'll try to give you a flavor of what it is. So when walking away from this presentation, you guys at least have some understanding. The second thing is the TensorFlow framework. It's not necessarily that you're going to be write full, complete programs in TensorFlow after this talk, but at least you'll get some core idea. And finally, I'll try to familiarize you guys with ways that you can learn TensorFlow and deep learning and use it, well, both of these things combined in your projects and research. So without further ado, let's get to deep learning. So deep learning is a branch of machine learning that specializes with artificial neural networks, which have become popular in the last 5 years and have achieved state-of-the-art results in many fields, such as image and voice recognition, NLP, and plenty of others. So let me perhaps give you a few examples of how TensorFlow, what types of problems you guys can solve with machine learning and deep learning in particular, and then go to a few more formal definitions. So you see two pictures, right? One is apple, one is orange, and I'm pretty sure all of you are able to tell which one is which, right? But tell me this, who's going to be able to write a program that's given a random image, is going to be able to spit out a label whether that image contains an apple or orange? Any hands? Well, somebody waved his hand, but, you know, we need to talk. Either you're a genius or we can talk about that. Anyway, but my point is that it's a pretty complex task, and writing such programs in C++, Java, Python, whatever language you're using is not such a trivial task, and that's where machine learning comes to rescue. It's machine learning and deep learning in particular are really great techniques and tools that you can use to address such problems. So on this slide you can see Google's Inception neural net, which Google uses to tackle the so-called ImageNet contest, which tries to classify a whole bunch of images into a taxonomy of around 1,000 categories, and you can actually look at it and see it's doing a pretty good job. I myself, to be honest, no lizard expert, but as you can see, the neural net's been able to do a pretty good job telling which lizard is which. Well, first of all, it's a salamander, and it turns out one of them is spotted and the other one is fire. I have no idea what it is, but that's what the neural net says, and apparently that's right. And to give you some numbers, the Inception neural net's been able to achieve something on the order of 95% accuracy on the ImageNet contest, which is comparable to what human raters are actually able to do. It's quite astonishing. Spam. Well, spam's been around us since perhaps the very creation of the internet, and in fact, there's far more spam on the internet than the real useful data. And machine learning basically makes the spam problem go away. So, in fact, these days, you almost never have to deal with spam. And that's in fact, a lot of thanks to machine learning. Another example is Google's Photos application. It's able to recognize what's on the image and come up with a text label so you can later categorize and group the images and use these labels to search for images. Quite useful because it relieves you of some manual job. Google's voice search, as I said, it's another area where where deep learning has been able to achieve state-of-the-art results. And to back it with some numbers, when Google deployed its deep learning model for Google's voice recognition feature, it's seen a jump of around 30% in the accuracy for the voice recognition. So now, in fact, I guess you guys are all using OK Google feature, right? Raise a hand if you don't. Well, yeah, just a few hands. Good sign. Apparently, it's been working well for you. And to give you a bit more info on this specific example, the neural net that Google uses to recognize your voice is actually running entirely on this small device. That is, you need no internet connection whatsoever with the cloud in order to be able to recognize your voice. And you can actually test it out on your phones if you turn on airplane mode and try to say something to it. You'll see. Nearly all Google's products use machine learning one way or the other, and this graph is sort of an illustration of that. It shows the number of directories which contain a description of a deep learning model at Google, some of which, well, a lot of which have been converted into TensorFlow or written in TensorFlow to start with, and currently TensorFlow and deep learning are used in around 60 major projects at Google. So that shows how widely Google has adopted it, and it also encourages you guys to use that in your projects, so everything is possible. So I hope you get a feel of it. So at least now you know what types of problems deep learning can solve. And now I'd like to get a little bit more into the sort of theoretical land and introduce a few core concepts of deep learning. So, as they say, everything new is well forgotten old, and so is the artificial neural nets. They've been around since the 1980s, and in fact, if you think about them, they're just a collection of small trainable mathematical units which learn to collaborate on solving complex problems, and can be easily used with a whole bunch of machine learning problems, such as supervised learning and reinforcement learning. So artificial neural nets are inspired by the way our brains work, and we say artificial predominantly because we're interested in the mathematical aspect of it, and we don't care about chemical reactions that take place here. Talk about the building blocks of the neural nets. They consist of neurons, which are, as I said, small trainable mathematical units which are connected to a small subset of other units, and they can recognize certain patterns of activity in their neighbors, and sometimes when they see something interesting, what their neighbors say, they can also be activated. And neurons are able to learn, to collaborate on learning how to solve a complex task. To put it in mathematical terms, the activation or the output of a neuron is a nonlinear function applied to a linear combination of inputs that are the neurons that this given neuron is connected to. And it's denoted by X here. And W is the weight matrix that is basically the importance of that this given neuron puts on other neurons. So as you see, it's a pretty simple unit, and some of you guys may sort of recognize logistic regression in this given the definition. But the simple logistic regression is not going to be able to solve any of the problems that I talked about earlier. But it turns out when you put together millions or billions of these neurons together and make them learn, they are able to accomplish pretty amazing tasks. And well, I say learn. What I mean by that here is when neurons learn, when the neurons in a neural net learn, they customize these weights, the W matrix, for each of the neurons. And that's exactly what's meant by learning. And this slide sort of illustrates the core idea behind it. So we're tasked with figuring out what's on the image. There's a nice pet in the basket. I want to know whether it's a cat or a dog. And we give it basically the raw pixels of this image to this neural net, to the bottommost layer of it. And some of the neurons of it somehow find something interesting in this picture, and they communicate this information up to the neighbors, and the neighbors also look at some of the activity patterns from the bottom layer, and so on and so forth. Eventually, we propagate the signal all the way up to the topmost layer, which allows us to conclude that it's, in fact, a dog. So now I'm going to take a sharp turn and talk about the TensorFlow framework. Can I actually raise a hand if you guys have had chance to use TensorFlow in any of your work? All right, well, a few people have. It's great. So TensorFlow consists of two words. It's flow of tensors, basically. And for the practical purposes, by tensors here, we mean multidimensional arrays of numbers. So a single number is a tensor. A matrix of numbers is a tensor. A cubic shape of numbers is also a tensor. And all of these shapes flow through a graph of operations. And what kind of graph I'm going to talk, well, right now on the slide. So what you do in TensorFlow, and what TensorFlow at its core, it's basically a graph execution engine. That is, what you do is you define a graph with some high-level language like Python that describes the computation that you want to make, and then this graph is compiled and optimized by the TensorFlow core, which decides how it's going to execute the graph. Say it can decide which computational devices it would want to put some of the nodes of the graph to, for example, CPU versus GPU, or maybe something else. And it makes sure that the tensors, your input data, is able to throw up and down through the graph, depending on what you're doing. The core is written in C++, and you never have to worry about it unless you want to actually change the TensorFlow framework. And it allows execution on a wide range of devices, starting from CPUs, which are the most traditional units, and all the way to tensor processing units, which Google announced at the latest Google I/O. And the front end that you use to define the graph. Currently, the front end can be described only in two languages, which are C++, the native implementation, and Python. But if you guys want to see your favorite language in the front-end languages, you are more than welcome to contribute. As I said, TensorFlow is an open source project. And now let's do a quick example. I'm going to show you a toy TensorFlow program just to illustrate some of these concepts and maybe make things a little clearer. So let's try to predict real estate prices by square footage. A pretty simple and straightforward task, I guess. All of you guys know what I'm talking about. And as with any practical machine learning problem, you basically perform 5 steps. You first collect the data. In our cases, these are going to be pairs of square footage and price. There may be something else. You can, say, scrape that from websites like, say, olx.ua or something. You choose, basically. And then you come up with a model that you think describes the data. And in case of real estate price prediction, it's pretty straightforward. It's just linear independence. You describe this model, this graph in TensorFlow. You train the model, and you predict the price. That's pretty much it. That simple. And here is how it looks in graphic terms. And the equation here describes y, which is the price, as w, which is the slope of this line, multiplied by x, which is the square footage, our input, plus b, which is the intercept term. And w and b are the parameters that we're learning for this model. You remember, like I said, you customize weights in big neural nets. You do the same here for this linear regression problem. So here's how the simple TensorFlow program that defines this graph looks. It's just 5 lines of code, and I'm going to just walk through all of them one by one to describe what they mean. First of all, you describe the variables that we're trying to learn. You specify the shapes and their initializers. Here we set the W and B to 1s. The second step, you define the placeholders, which are your inputs. And last but not least, you describe how these are combined together to produce the output. And as you can see, this formula, well, this line actually implements the formula that you've seen a few slides earlier. Y equals W times X plus B. And the graph that you end up with is shown on the right-hand side. And that's it. You've defined your basic. Well, here, someone applauded. OK, well, someone else did. Yeah, and that's basically how you define a basic graph in TensorFlow. The cool thing about it is the fact that we're just one step away from defining a trivial neural net. You remember a few slides earlier when I defined some concepts of the neural nets, there was also non-linearity applied to the linear combination of inputs. So you just put some non-linearity on top, and that's it. You're done. You have your basic neural net. Well, now you want to execute the graph to get your predictions, and that's how you do it. You feed in some data. So in this case, it's going to be, say, a vector, column vector 3, 4, and you run the y node of the graph, and the computation that you end up with is shown on the left. You multiply the 2 vectors, and you add 1 to it. You end up with 8. That's simple. But the second step, well, in fact, I described it as step number 4, if I'm not mistaken, in my general outline slide for this problem. You want to learn W and B. And, well, the way you learn it is as follows. We will compute the distances from the predicted values to the actual values that we know. And that's shown, that basically corresponds to this distance line. Then we square the distance so that we don't have to worry about the sign. And last but not least, we will add all of the elements of the squared distance tensor together. Note that these 3 lines, in fact, add 3 additional nodes to the TensorFlow graph that I showed you on the previous slide. And the next step you do is you just need to apply an optimizer to minimize the cost. This way, fitting the line to your data set. And what we're using here in this example is a gradient descent optimizer, which will take care of computing gradients and, well, computing gradients automatically, I should say, and minimize the function. Now, in order to actually find the parameters, you have to execute this graph. And the way you do it is just, it's enough to run the update step node, which is just the minimization of the cost a sufficient number of times. And this will take care of learning W and B. And that's it. Well, as you can imagine, it's a pretty simple and straightforward program, but hopefully it gives you some understanding of what TensorFlow is and how it works and how to write programs in it. But I just wanted to tell you a bit about the tools that we have. And one of the most important tools is the tensor board. Debugging and figuring out what's going on with the learning process is a pretty cumbersome task if you don't have any insight into what's going on. And TensorBoard actually gives you that insight. It plots you a whole bunch of different metrics, such as loss and the distributions of your weights that are currently learned by the system on a nice dashboard. And you can monitor them and make sure that you take action if things go not the way you expected. Setting up TensorBoard is just 2 lines of code and running something on the command line, as shown at the bottom. OK, and last but not least, I wanted to tell you about the ways you guys can take care, we can approach deep learning with TensorFlow. Well, doing deep learning with TensorFlow and maybe using it in your projects. Well, first of all, we have Playground, which is a simple neural net that you can train directly in your browser, play with architecture, weights, and a whole bunch of other parameters. Totally worth spending 30 minutes playing with it and seeing what it can do. Second, we have a whole bunch of tutorials, which range from the very beginner MNIST problem, which is the hello world of machine learning for recognizing handwritten digits, to some complex sequence models. It's worth to mention that out of 10 of these tutorials, only 2 are provided by Google itself. The rest were provided by the open source community, so you guys are also welcome to contribute here. The white paper, if you guys want to learn the details and specifics about the core of the TensorFlow and how it works. And if you want to use TensorFlow in your project, here are some options that trade off on flexibility and the amount of effort you have to put in to use them. First of all, you can use our cloud APIs. And in fact, I've seen a few of you guys actually playing with the Vision API. I'll just show it once again so you guys can see the kinds of things you can do with the Vision API. As you can see, it can recognize and summarize the images that you feed into it with some scores, as well as it can tag certain events or objects in the images with, again, some scores and descriptions. Second, you can use pre-trained models. For instance, you can easily download the pre-trained inception model and use it to recognize objects for you. And the way you do it is as simple as 8 lines of code. You load your model on your device, well, for instance, this device, assuming it fits on this device, and then you run predictions on the model that you loaded. Third thing is that if you have a lot of data, you can certainly try to train your own models. It's a little bit of an involved thing to do, but you're totally welcome to try that out and see how that works. But keep in mind that for that, you'll need your own machines or some virtual hosts on some sort of a cloud environment. Or, well, assuming you can get to it, you can also try out Google's machine learning API, Cloud Machine Learning API. And last but not least, for those of you guys who are more advanced and want to do some research, you are welcome to try out developing your own crazy ideas and experimenting with it in TensorFlow. As I said, TensorFlow allows you to express all sorts of crazy ideas that researchers have come up with. So you're more than welcome to do that and try it out. And this slide concludes my talk. I guess thanks, and now it's the Q&A time.
Okay. Hello, my name is Bogdan. First, thanks for the very wonderful presentation. Now, with predicting the price of an apartment based on how large it is, you came out with your model. Now, when you detect a cat on a picture, how do you build a model?
So the linear regression model that we use to predict prices, as I said, it's a toy example. So I just use it for demonstrating you guys how to write simple TensorFlow programs. As for the cats and dogs examples, you build complex neural nets for that. And in fact, if you want to build your own model for that, it's a long topic of it basically takes you a long time to learn these things. And you have to go into theory of machine learning if you want to be able to do it yourself. But my recipe for you, if you want to just try things out quickly on the data sets, is just download some existing models, like Inception, which are known to work well, and try to play with them.
Any other questions? Okay, I see a hand.
Do you know if there are any bindings for Node, for instance, if I can use this thing in a JavaScript project?
Can you repeat that, sorry?
So do you know, you said we could use pre-trained models, and then for the front end you had Python bindings, and I don't know what else the second one was. And I was curious if there are any TensorFlow bindings for Node, so for using this thing in JavaScript projects.
I believe currently the two supported languages are C++ and Python. We don't have anything, unfortunately, in either Node or any other language. So as I said, you guys are welcome to contribute if you want to have that available. But sorry, only Python and C++ for now.
That's OK. It's cool work. Thanks.
Yep.
Okay, next question. Okay, see.
Hi, I'm Victor. I'd like to ask a question about specifics of using TensorFlow with Android operating system. So basically, what are some kind of specific things that you should do to run models on Android operating system?
Nothing. Well, of course, there are some limitations. You have to make sure the model fits on your device and it doesn't eat up all of the computational resources. It's not that big. But TensorFlow was designed with the portability in mind. That is, you can train your model, say, in the cloud, and grab the serialized version of that model, deploy that as is on a mobile device, and have your Android app read the model and basically use it out of the box. And that's why I said nothing.
Are there any examples available on the internet from Google?
I believe there are some. I can't give you any specific example now off the top of my head, but I believe if you check out the TensorFlow website, I'm pretty sure you'll be able to find a few.
Okay. Any other questions? Questions? Put your hands up. Okay. Okay, thanks, Rustem.
Thank you, guys.